Welcome back to the Mechanics of Solids lecture series. We're working on examples related to torsion in indeterminate shafts and thin-walled tubes. We'll continue with the example we were working on last time, a segmented tube in series with internal torques applied. We found two equilibrium equations and a compatibility equation that we can use to solve for the internal torques. Let's start off by manipulating the terms in the compatibility equation a little bit more. And I'm going to go ahead and substitute for some of the known values. I think it will simplify the work later on rather than carrying all those terms through. So I'm going to solve for L1 over J1 G1, which we note is equal to L3 over J3 G3, which is equal to the length of those segments, 12 inches, divided by the polar moment of inertia for a solid section is pi over 32 times the diameter to the fourth, 2.5 inches in this case, and then times the given value of the shear modulus, which was 4,000 KSI. This computes to a 7.823 times 10 to the negative fourth. And if you look carefully here, the units are per kip inch. We have a kip on the bottom. We have inches cubed from the square inch and the inch. Inches cubed on the top and inches to the fourth on the bottom, which reduces to this. Okay. I also want to find L2 over J2 G2, which would similarly be computed as 24 inches. Pi over 32 times the diameter of that section to the fourth times the shear modulus of that section, and this computes to a 4.643 times 10 to the negative fourth per kip inch. Okay, now substituting those values into the compatibility equation, which I will kind of start over here. I have the 7.823 times 10 to the negative fourth per kip inch. Notice that multiplies T1 and also T3. So I will add those together, T1 plus T3. Plus I have the 4.643 times 10 to the negative third, which multiplies T2, and I set that equal to 0. This is also per kip inch. I'm going to simplify here a little bit by noticing that the e to the negative 4 and the per kip inch carries through the entire equation. The right hand side is equal to 0, so I can cross those out and eliminate those without any loss of information. Okay, so now this simplifies a little bit, 7.823. Now I'm going to substitute the equilibrium equations for T1, which is TB plus T2, and then for T3, which is T2 minus TC, and carry this over plus 4.643 times T2. Let us now isolate the terms that multiply T2. We have a 2 times 7.823 plus the 4.643. This whole thing multiplies T2, and we're left with 7.823 times TB, which is 20, minus TC, which is 40, gives us a negative 20 kip inches. Set that equal to 0. Now I can solve for T2. 7.823 times 20 kip inches divided by that whole thing, which computes to 20.289, and this simplifies to 7.49, and the units of kip inches carry over, so that's T2. T1 we would find from the first equilibrium equation. T sub b, 20 kip inches, plus the 7.49 kip inches, gives us 27.49 kip inches. T3, which we get from the second equilibrium equation, is T2 7.49 minus TC of 40, both in kip inches, equals negative 32.51 kip inches. Okay, so those are my torques, internal torques. Now I wish to solve for the stresses in each segment. I can get the stress from the stress to torque relation. Tau equals TR over J. Remember, this is the maximum shear stress that occurs at the outside outer radius. Let's solve for T1. T1 equal to the torque of 27.49 kip inches times the radius, half of the diameter, 2.5 inches over 2, divided by our polar moment of inertia, pi over 32, 2.5 inches to the fourth, which computes to 8.96, and then units are kips, inches squared on the top, inches to the fourth on the bottom, so reduces to inches squared and gives us a stress in KSI. For expediency, I'll skip the calculations for the other two. Tau 2 is equal to 1.41 KSI. Tau 3 is equal to 10.60 KSI. Notice the problem asked for magnitude. I'm not concerned about the sign. So those are my answers for Tau 2, Tau 3, and Tau 1. I may have said earlier that Tau 1 and Tau 3 were the same, but that was a mistake. They have different internal torques, so different stresses. Okay. Last part of the problem asked to compute the rotation angle of joint C. In terms of compatibility and what's happening in the problem, the left end is fixed, the right end is fixed. So the rotation angle of joint C we could get by either computing the internal rotation in joints 1 and 2 and segments 1 and 2 and adding them together, or compute the rotation of segment 3, which will give us the rotation of joint C with respect to D. I think the latter approach is simpler, so I will proceed with that approach and calculate V sub C equal to phi3. I'm not going to worry about the sign, just find the magnitude of the rotation. This comes from T3 L3 over J3 G3, or the TL over JG equation. The torque we know as 32.51 kip inches. We solved for it in the previous part. We also, if you recall, solved for this number L3 over J3 G3 to solve the compatibility equation, and that was equal to 7.823 times 10 to the negative fourth per kip inch. And those units cancel out, giving us units of radians, which is what we expect, and the number is 0.0254 radians. It's a reasonably small value. Our stress magnitudes were in the range of 5 to 10, also reasonable magnitudes for a torsion problem, and so our answers pass the logic check.